Well, first of all, thank you to everyone for being here. And today I'd like to do two things. First of all, to introduce the B field transformation. And second, so with the goal of defining what we mean by generalized complex submanifold. And we'll see that in contrast to the non-generalized case, in generalized complex geometry, even the definition of a submanifold is going to be a little bit subtle. Also, I just want to remind everyone of one of the definitions that we're going to be using quite centrally here. So two things. First of all, that the extended tangent bundle T, and that's with two lines. So blackboard bold for, I think, for the TM is the direct sum of the tangent bundle and the cotangent bundle. So it's sort of like we're augmenting the directional information of the tangent bundle with this additional dual information. And then on the extended tangent bundle, we define the, or on sections of the extended tangent bundle, we define the Courant bracket, which is given here. So I'm just going to leave this up because I think it's a little bit different, not so straightforward to remember. Okay, so jumping right in with the definition of B-field transformations. A B-field transformation on a generalized complex manifold M strict J is a closed two-form, is just a closed two-form B. So in fact, in the construction of a B field, I'm sorry, a B field, not transformation. A B field is a closed two form on our generalized complex manifold MJ. But note that we don't even really need the information encoded in J here. So we can define B fields just on smooth manifolds M. And then we identify, so as a note, B with the fiber endomorphism, the fiber transformation, or fiber map on TM on the extended tangent bundle given by sending an element x plus alpha. So here x is an element of is a tangent vector, and alpha is a dual tangent vector based at the same point as x, and sending this to the interior product, or the pairing of x with B, with the B field. And we're not going to use this map so much, rather we're going to use its exponential. So note that the exponential of B interpreted as a fiber map in this way its value when or its value in x plus alpha is the sum as k goes from 0 to infinity of x B over k factorial, which is x plus alpha. This is the k equals 0 part, plus ixb, the k equals 1 part, plus terms involving multiple interior products with x. So all of those terms are going to vanish, and we're left with x plus alpha plus the interior product of x with b. And now we define it, so now we're in a position to define the B field transformations in the following way. So the B field transformation associated to our two-form B is given by the fiber map on the extended tangent bundle described by the exponential of B. And so today we'll have one proof, and so that proof will go with the following proposition, namely that the B field transformation is a automorphism of Courant algebroids. So it's a Courant automorphism. So what this means is three things. First, that pi of EB x plus alpha is equal to pi of x plus alpha, so we need to show three things. The second is that the symmetric bilinear pairing, non-degenerate symmetric bilinear pairing of the transformation applied to x plus alpha, and applied to y plus beta is equal to the B field transformation applied to, is just equal to the pairing between x plus alpha and y plus beta. And thirdly, and the most complicated one, is that the Courant bracket, or the Courant bracket applied to the B field transformation of x plus alpha and y plus beta, respectively, is equal to the B field transformation applied to the Courant bracket of x plus alpha and y plus beta. Okay. So the first is the easiest. We have, this follows immediately as pi of x plus alpha plus ix beta is equal to x. So recall that pi being the anchor map of the extended tangent bundle as a Courant algebroid is just the projection to the tangent fibers. So these are sections of the dual tangent bundle. X, a vector field, is a section of the tangent bundle. But that's just the same as pi applied to x plus alpha. And so this is what we wanted to show. Oh, and then, of course, this here is the B field transformation applied to x plus alpha. So, done. Second, we want to establish this equality here. And we see that, that gives us x plus alpha plus interior product of x with beta on the left-hand side of the pairing, and y plus beta plus the interior product of y plus the interior product of y and b on the right-hand side of the pairing. And then recall how the pairing is defined. So this is going to be one half of the contraction of x with this expression here, plus one half of the contraction of y, fiber-wise, with this expression here. And what's going to happen, I'll write it out. So this is going to give us, let's see, so one half x plus alpha, x plus alpha, y plus beta plus one half interior product of x, interior product of y beta, plus one half interior product of y, and an interior product of x, sorry, not beta, but b. And these are the negative of each other, so they go to 0. And then this equality, and so then the equality that remains is that which we intended to show. So we will check. And now for the most involved one, C, we want to show that the B field transformation is an automorphism of the Courant bracket. So this will take, I think, like 2 steps. So first, I'm going to label the right-hand side here as star. So in case that's not visible, this term here is star. And then note that star is equal to the B field transformation applied minus Ly beta minus 1/2 exterior derivative of interior product of x beta minus interior product of y with alpha. So this here I'll make bigger brackets. This here is just the definition of the Courant bracket. So I've just substituted for the Courant bracket here. It's written out expression. And now note that all of these terms combine to form a section of the cotangent bundle, and this first term is the projection to the tangent bundle, or to a section of the tangent bundle. So now it's clear what the result of the B-field transformation is going to be. It is this term here that is the projection to the tangent bundle, plus the interior product of, it's going to be this entire term plus the interior product of the projection to the tangent bundle with B. So that gives us the Courant bracket of x plus alpha, y plus beta, plus the interior product of the Lie bracket with the B field B. So we're going to use this expression here. So now we have sort of a computation. We want to show that the following expression is equal to 0. So let's say plus the B-field transformation applied to x plus alpha, paired by the Courant bracket with the B-field transformation applied to y plus beta, minus the B-field transformation on the Courant bracket of x plus alpha and y plus beta is equal to, and again, so we want to show that this is 0. So this part here, this is star. We've shown that it's equal to that expression on the right-hand side there. So rewriting both terms here, we get that this is equal to the Courant bracket of x plus alpha plus interior product of x with b, y plus beta plus the interior product of y with b, minus, and now plugging in for star, Courant bracket of x plus alpha, y plus beta, plus the interior product of Lie bracket of x and y with b. So I'm not going to write out every single step, but note that what we'd like to do is to rewrite this term here in terms of 4 terms involving these bracketed, these underbracketed expressions and the interior products here. The first term, if we expand that out, involving the underbracketed expressions, is going to cancel with this negative term here. So we end up getting, likewise, any terms, two of the other terms that we get when we expand out, which involve only sections of the dual tangent bundle, are also going to vanish because the Courant bracket vanishes when there's no, or on terms that don't involve any section of the tangent bundle. So actually we end up just getting one term here. and that is, or I'm sorry, two terms, and those are the current bracket of x and the interior product of y with b plus the interior product of x with b with y. And so then that first term vanishes, or the first combination vanishes, and then we have this interior product with the Lie bracket here. So that's xy with b. And let me just check my notes really quick. Okay, sorry, this should be, so I made a mistake. This here should be a negative sign because we're subtracting the expression star. So I'm going to rewrite that negative. Likewise, this plus sign should be a negative sign for the same reason. There we go. So then using the definition of the current bracket, we get it written up here. We get, so writing it out, we have the Lie derivative of along x of the interior product of y and b. Let me see, minus, so here I'm writing the first term, minus 1/2 the exterior derivative of the interior product of x with the interior product of y with b. So again, these two terms are equal. Plus, and now we're going to have a precisely analogous term, except we're going to switch the role of x and y, and we're also going to pick up a negative sign. So that gives us actually minus the Lie derivative along y of the interior product of x and b plus 1/2 the exterior derivative applied to the interior product of y, the interior product of the interior product of x and b, minus this term here, so that's the interior product of the Lie bracket of x and y applied to b. And this looks pretty terrible, but we're going to clean it up. So we're going to do that by recalling that the interior product of x, the interior product of the Lie bracket of two vector fields applied to a differential form is the commutator of the Lie derivative of the first vector field and the interior product with respect to the second vector field applied to that differential form. And then we're going to note that the first expression, or the first term in that commutator appears over here, and because we have a subtraction here, that's going to cancel. And that's going to leave us with an interior product of y applied to the Lie derivative along x of b over here. So I'm gonna write out what we get then. So that's again the interior product of y of the Lie derivative along x, and I'm not going to write the b here. I'm going to move all of the b's to the end of the line. So minus minus the exterior derivative of the interior product of x and the interior product of y with b, which is going to go over here. And so here, what I've done is I've combined both of these 1/2 exterior derivatives note that the order of the application of the interior products with respect to x and y is switched. So these are negatives of each other, and so they combine to replace the 1/2 with 1. Let's see, so, and then minus the Lie derivative along y of the interior product with respect to x of b. And so in this case, I haven't changed it at all. I haven't modified it. Right, so now we have this expression here. It's somewhat simpler. It still doesn't look that great. So now what we're going to do is we're going to use the Cartan's infinitesimal homotopy formula to replace both of the Lie derivatives with exterior derivatives and interior products. And so that gives us the interior product of, or with respect to y, the exterior derivative applied to the interior product with respect to x, plus, or actually I'm just going to write it out, and then comment on it, minus x, y, minus, let me see. So that's 1, 2, 3, 4, 5. 1, 2, 3, 4. Good. Oh, and just to be explicit, so the substitution that I used was that Lie derivative along x of b is equal to the exterior derivative applied to the interior product of x and b plus the interior product of x applied to the exterior derivative of b. And then the analogous formula in terms of y and b. All right, so now we have some cancellation. An obvious cancellation is that this first term is the negative of the last term, so they combine to give us 0. The next cancellation is to notice that here the order of application of interior products with respect to x and y is inverted, is switched. So those are negatives of each other, and they combine to form, to give us 0. And then we're left with the interior product of y of the interior product of x with the exterior derivative of b. So that's y x db. And this is equal to 0. So this is equal to 0 if and only if the exterior derivative, this expression itself is equal to 0. Oops. This is, of course, for all vector fields x and y. Part of the definition of the B field B is that it is a closed two-form, so we're done. So we have established equality C. And again, just as a reminder, what we've done here is to show that this fiber-induced transformation on sections of the generalized tangent bundle is an automorphism of the generalized tangent bundle as a Courant algebroid. And then it's a fact. Oh, so this is the end of the proof. And it's a fact that every automorphism, every such automorphism of the generalized tangent bundle as a Courant algebroid is a composition of diffeomorphisms. So one, transformations induced by diffeomorphisms of the underlying manifold M, underlying smooth manifold M, to B-field transformations. And this is in contrast with the Lie bracket on the non-generalized tangent bundle. In the case of the Lie bracket, every automorphism as a, I believe, as a vector bundle, is induced by, or as a Lie algebroid, I think, is induced by diffeomorphisms of M. There's no analog of B-field transformations in that case. Okay. So now I want to define what is meant by twisted generalized complex structures, but first we'll take a short break and I'll erase the boards. All right, so section 2 is twisted generalized complex structures. So the idea here is that we're going to modify or adjust the data encoded in the generalized tangent bundle in such a way to modify the conditions that define when we have a generalized complex structure. And so here, with the generalized, when I say generalized complex structure, we're going to be viewing it as a maximal isotropic Courant integrable section of the complexified generalized tangent bundle. And so I'm going to write all of this out and it will make more sense. Right, so first of all, we're going to fix a closed three form H, so closed, on M, and it is with respect to this closed three form H that we're going to twist, that we're going to define a twisted generalized complex structure, and we're going to do that by means of first defining a twisted, the twisted Courant bracket on the generalized tangent bundle. Okay. So, definition. The H twisted current bracket on the generalized tangent bundle is given as follows. So we're going to use these double brackets again, double brackets x plus alpha, y plus beta. And once more, x and y are sections of the tangent bundle. Alpha and beta are sections of the dual tangent bundle. Subscript h for h twisted is defined to be the ordinary current bracket between x plus alpha and y plus beta, plus the interior product of y and the interior product of x with h. And now note that since h is a 3-form, this double interior product means that this expression, or this term here, lies, or is a section of the dual tangent bundle, or the cotangent bundle on M, and so it makes sense to say that this left, or that, sorry, that this right-hand side is a section of the generalized tangent bundle. Oops. And then it's a fact that with this h-twisted bracket, the generalized tangent bundle Tm becomes a, along with the other data unchanged, is a Courant algebroid on M. And so we had defined abstractly what a Courant algebroid is 2 lectures ago. Briefly, it's a vector bundle E over M with the following. So this would be E with a anti-symmetric pairing, not necessarily Lie bracket H, a bilinear pairing on sections, these angled brackets, and an anchor map pi from E to the tangent bundle, satisfying 5 compatibility conditions, which take a full board at least to write out. So I'm not going to write them out again. But in any case, this H-twisted structure is again an example of a Courant algebroid. And so now it's very easy to define what we mean by an H-twisted generalized complex structure. It is just, or it's defined to be by as follows: an H-twisted generalized complex structure on M is a fiber-wise assignment of linear generalized complex structures to the fibers of the generalized tangent bundle, or extended tangent bundle, And now such that, so recall that previously, we have a local compatibility condition given by the fact, or the condition that the plus I eigenbundle of the assignment of generalized complex structures, or linear generalized complex structures J, that plus I eigenbundle in the complexification of Tm is Courant integrable. Now we're going to require that it be H-twisted Courant integrable. So such that the plus I eigenbundle of J, let's call it L, so that lies in the complexification of the extended tangent bundle is integrable with respect to the H-twisted Courant bracket. And that's it. So now section 3. So we're going to see this come back, or this construction come back when we talk about generalized complex submanifolds. But now we're going to jump to the generalized tangent bundle of a smooth submanifold of a generalized complex manifold. So section 3. The generalized tangent bundle of a submanifold. So now we're going to let M be a submanifold of N. So smooth submanifold. And we define the generalized tangent bundle of M, or of this inclusion, to be tau sub M, given as the fiber-wise direct sum of the tangent fibers, or of the tangent bundle, and the annihilator of the tangent bundle 2M, I'm sorry, the annihilator of the tangent fiber Tm, or Txm, in the ambient tangent fiber, ambient cotangent fiber T star n. So I'm going to write that down. So annihilator of T m, and this is a sub. Well, it's a assignment of subspaces to the cotangent bundle of n along M. So maybe a picture would be helpful here. Let's see. Oh, and then this is a subbundle of the restriction of the extended tangent bundle of n along the submanifold M. Okay, let's see. So here is N, the ambient manifold, and then within which we have a submanifold M. The fiber at X in M of tau M is the direct sum of the tangent fiber at X to M. So that is a, I'll draw it down here. Here's that, or here is the tangent fiber at X to N, within which lies the tangent bundle, or sorry, the tangent fiber at X to M. So that in this picture is this one-dimensional space. That's one of the summands, and then the other term is the annihilator of this subspace. So the annihilator at this point X of this subspace in the dual tangent in the cotangent bundle at X of N. So that's going to consist of all linear forms which vanish, or so all linear forms on, or all covectors on Txn, so on this vector space, which vanish on the subspace tangent to M. Okay. And so, okay, I'll give two, well, let me see this time. Okay, yeah, I'm going to give a preliminary definition of what we might want to define as a generalized complex submanifold. I'll give two examples of that, and then I'll describe why that definition isn't the optimal one, and then I'll present the optimal definition. And I guess I should say, as I've said in the previous lectures, so all of this material is taken pretty much directly from Cavalcanti's monograph and Gualtieri's thesis. Okay, so preliminary definition here. And I'll write it out. So we might be tempted to define a generalized complex submanifold as a smooth submanifold M in N or I guess I should say a generalized complex submanifold of N J such that the generalized tangent bundle tau M as a, let's say, subbundle of the extended tangent bundle of n restricted to m is preserved by the generalized complex structure J. So now I'll give two examples two examples that satisfy this preliminary definition. So we're going to see, or we'll state why this definition isn't, or actually we can do that now. So this preliminary definition isn't optimal because it's not compatible with B-field transformations, namely. If we apply a B-field transformation to a generalized complex structure, or to the data over a submanifold, we don't preserve the property of being a generalized complex submanifold. So examples. Let's see, example A for the standard example obtained from an actual complex structure on M. So here I is a fiber endomorphism of the tangent bundle, which is a complex structure on N. And we have that the generalized tangent bundle to M is preserved by J if and only if the complex structure that induces J preserves, as we can see, this is split here, so it preserves the tangent bundle to M, and that's a subbundle of the tangent bundle to N along M. And that is what it means for M to be a complex submanifold of N. So that's if and only if M is a complex submanifold. Okay, the second example at the other extreme is that our generalized complex structure J is induced from a symplectic structure and in this case, the generalized tangent bundle Tm is preserved by J. J omega if and only if these two conditions hold. So note here that this generalized complex structure, as opposed to the first one, so the first one preserves both factors. It preserves the tangent bundle and the cotangent bundle fibers. In the case of a generalized complex structure induced by a symplectic structure, we exchange the tangent and cotangent fibers. So in this case, we need we need this map to send the tangent bundle into the annihilator of Tm. Let me see. Because we're sending Tm, so we're sending this factor into this factor, and we need, and so then in the other direction, we need the inverse map to map the annihilator entirely into the tangent bundle. And the first condition says that pairing anything with, let's see, so the first condition says that pairing anything in Tm, in this subspace of the tangent fiber to N, with anything else in the tangent fiber to the subspace M is 0, because it lies in the annihilator. So that means that omega vanishes on this subspace, which is to say that the subspace is isotropic. The subspace is isotropic. And this is how we define an isotropic submanifold. M in N, isotropic. Similar reasoning shows that similar reasoning applied to the second case means that M in the tangent bundle to M as a subspace of the tangent bundle in the linear symplectic space. The fiber of N is co-isotropic. So M is a co-isotropic submanifold of N. And a submanifold that is both isotropic and co-isotropic, well, that's the definition or condition in symplectic geometry to be a Lagrangian submanifold. So that's if and only if M and N is Lagrangian. So this is quite nice because it says in some sense that this, at least this naive definition, gives us in the complex case the complex submanifolds, and in the symplectic case the Lagrangian submanifolds. But then, as noted, this isn't the correct definition. So I'll give the definition of a generalized complex submanifold, and then I think we'll be done at that point. So section 4, generalized complex submanifolds. So we're going to consider the following data. a smooth submanifold M in N a closed three-form H on N I'll write it this way. On N, so DH vanishes, and a two-form, not necessarily closed, on M. And a illustration, or just to see where everything lives. So here is N, the ambient manifold. Here is M, the smooth submanifold. Make that clear. F lies on M, and H. So H is a closed three-form on N. F is a F is a two-form on M, on the submanifold. Great. And we say that so we say that the pair MF is a generalized submanifold of NH if the exterior derivative of F, so that's a three-form along the submanifold, is equal to the restriction of H to, so here we're thinking of H as a section of the exterior of the exterior algebra bundle of the cotangent bundle on N. We're restricting those fibers to M. We're not considering the pullback of H2M, I think. So if we have this equality. And then we'll note that the B-field transformations act on the extended tangent bundle, or the generalized tangent bundle tau M in the following way. So note B-field transformations act on tau M by EB acting on MF is given by the pair M with the two-form F plus the B-field F plus the B-field B. So B is a two-form or closed two-form. F is also a two-form. So this is again a two-form. So it fits into it is the type of thing that can be a generalized submanifold. However, I see that I have forgotten a definition here. So this note should actually come after this definition, and that is the generalized tangent bundle to a generalized submanifold. So previously, here we defined the generalized tangent bundle of a actual submanifold. Here we're going to define the generalized tangent bundle of a generalized submanifold. So that's a submanifold paired with a 2 form, which when the exterior derivative is taken of that 2 form, we get the restriction of the 3 form that is associated with the ambient manifold. So the generalized tangent bundle of the generalized submanifold MF in NH is tau MF given by all elements x plus alpha. So x, as usual, is a, okay, so x is going to be a tangent vector, and alpha is a cotangent vector based at the same point as x. So this is in the, so this is specifically in the direct sum of the tangent fiber to M, that's the tangent fiber to the submanifold, with the cotangent fiber to the ambient manifold restricted to the submanifold M, such that the restriction of alpha in this second factor is equal, or the restriction of alpha to M is equal to the interior product of X with F. Let me see. Okay, so to be clear, I don't have a terrific intuition over what this is sort of representing, but here it is. And then, all right, and then so then our final definition, our final construction here is we say that the generalized submanifold MF of our ambient manifold N, which is now a generalized complex manifold, so paired with or associated with a generalized complex structure J, and our twisting 3-form H is a generalized complex submanifold so this is the real definition, is a generalized complex submanifold when the generalized tangent bundle of this generalized submanifold is preserved by is preserved by the generalized complex structure J. And that's it. So it looks like it turns out that in this, that with with this extended definition, or this more general definition, the class of examples is much larger. But as I said, I have not much intuition over this material here. I think maybe it's helpful to think about it as, or in terms of a generalization of the more compelling original preliminary definition that we gave prior. All right, so that's everything. And then what I'd like to do, so I think this is the last lecture where there's new material. So this is actually the end, well, almost the end of Gualtieri's thesis, though we certainly haven't covered anywhere near all the material. But I think this is the last bit of sort of foundational material that I'd like to present. And then we'll have a review next week where we'll go through and sort of highlight the what we've seen so far, but we'll do so with the benefit of hindsight and understanding this time where, or what the idea of many of the constructions that when we first saw them we weren't completely sure what their relevance was. Now we do. So we'll have maybe a more cohesive presentation of a lot of that material, and then after that maybe take a break and look more at research direction. So personally, I'm interested in or I'm intrigued by these some of the material that I've seen relating to quantization and gerbs and branes, B-R-A-N-E. Then it looks like it's relevant to physics. All right, so are there any questions?
In the definition of generalized manifold,
Yeah.
when alpha restricts to m, it means to Tm.
Yes, yeah, that's right. Well, I think that's right. Let me see. Oh yeah. No, that's absolutely right. Thank you. Yes, that was a mistake. So yeah, I was actually wondering about that when I read it, of what it might mean. Any other questions? Yeah, I think this is a little bit open. I think this is worth thinking about a bit. Right. Well, if there are no other questions, then I'll see you next week.